Okay, so to start this demo, the first thing we're going to do is create a brand new project. And you can see we've got some templates here. We'll just save a bit of time, we're using a template. This one is going to be a USB authentication device that uses a security EEPROM chip from Atmel. So we'll go ahead and create that. Note that I can add any project level parameters to the project, and those can be accessed in documentation later on if we want to, or things like schematic title blocks and so on. So when I create that, it creates a copy of the template files, and in this case the template includes not only a schematic template, which includes the necessary USB connector and protection devices, it also has the template for the PCB. Now you can have individual document templates, or you can have whole project templates like this one. This one even includes a mechanical enclosure for a USB thumbstick and all the basic components needed for the USB Type A connector. And what I want to do right now, just to keep things out of the way while I'm getting the PCB ready later on, I'm going to make the 3D model for the enclosure as transparent or hidden right now. Also, we have a bill of materials document, and the components will automatically find their way into that as we add them. So to get started with, the core of this device is a microchip MCP2210, which is a USB 2.0 to SPI bus bridge. And I can place that straight from my library there. And note that the orientation of the USB signals is reversed there, so I'll make a crossover connection on that later. The next part we need is the 12 megahertz crystal that goes with that USB bridge. And one of the cool things about Altium schematics is you can butt pins up against each other and then drag, and it automatically maintains the connection, as you see here. Then of course I need my 18 picofarad load capacitors for the oscillator. So I'll place those on either side, and using shift, click and drag makes a copy of that part on the schematic, which is really cool as well. What else do I need? I'm going to need some decoupling caps. So I'll use the one that's part of the template here and use that shift, click, drag to make copies of it. So I'm placing 2 of those for the bridge chip. It needs 2 decoupling caps in parallel at 10 nanofarad, and I also need a 220 nanofarad decoupling cap for the internal regulator that creates this VUSB power net, which we're not actually using, but it still needs to be bypassed from within the chip. So that's what that capacitor is there for as well. Now I'm placing some grounds around the place. I'm going to wire up, here we go, wiring up the ground connection to the crystal and the load caps. Should just take a moment here. Okay, then I'm going to connect the other side of the oscillator connection to the other side of the crystal. And I'm going to place a VCC up here because we're going to use that as a pull-up on the reset pin. And again, drag that out to maintain the connection. And the USB is going there to that decoupling cap. The VDD connection goes to those decoupling caps and to the VCC connection up there. And then all of these caps on the other side and the VSS pin are going to go to that ground net label there. So I'll just wire those caps up. Okay, there's that. Now I also need some other stuff for this design. I'm going to put in the component. I need some 10K pull-up resistors here, so I'm going to find a 10K. There's a few in the database, but that first one looks pretty good. I want to pick the nominal sized footprint for the IPC footprint styles. I need one down there. That's going to be, that one is going to be for the reset pin. And note that when I plopped that resistor down there, it automatically inserted itself in that wire and broke the wire apart and put itself in there. So I now have a 10K pull up to the VCC for that reset. This other one is for a push button switch, which is going to go down here. And I need a VCC and a ground for the push button. I need one down here because later on I'm going to place a RGB LED down here in this corner. I'm going to need another VCC for that, and let's see, let's find that. It's I need a 10 ohm anode resistor just to provide a bit of filtering on the LED so that it doesn't interfere with the rest of the circuit. It's probably not really necessary, but I'm a stickler for this kind of thing. So I'm going to place a 10 ohm resistor there and a 1 microfarad capacitor to provide a bit of switching isolation for the LED currents, because LEDs, 20 milliamps or so, or 5 to 20 milliamps they draw, and I don't want that to put too much noise on the VCC, since this is a bus powered USB device. There's no external power supply or anything like that. So that's going to come out to the anode of my common anode RGB LED chip. So LTST C19, there it is. There's my RGB chip in the library, so I'll place that one there. Okay, I'll drag it over a little to make some room for wiring it up to the GPIOs of the bridge. Now, something you can do, I'll just show you this really quick. You can drag wires around, and using simple shortcuts in the Altium schematics, you can do cool things like bring a whole bus of wires around a corner. You can change wiring modes. I'm just cycling through all of that using shift space as I do that. I'll actually just manually wire these up now. Let's start with the USB signals, and I'll change to the 45-degree corner mode so I can make a crossover. GP 1 through 3 are going to be used for my blue, red, and green LED chips, respectively. So those are wired up. But I will need to insert some dropping resistors into those. So I'm just going to move those over by selecting. You can see you can group select and drag those wires. And some other cool things here, if I select and grab the end of one of those and drag it, all of them drag together intelligently. So just some of the wiring features of Altium Designer save you a lot of time. Up here is where my encryption device is going to go later on, so I'll place the VCC and ground there ready for that. And again, yes, I know I'm shorting out VCC to ground, but what I'm going to do is place a capacitor there for the decoupling of that device, and it inserts itself. GP0 on the bridge is going to be the chip select for the SPI bus for that chip. Okay, now I need to place a VCC pull-up for that push-button switch and wire that up. And that's going to go to GP4. So we'll use that as an input from the push-button. The bottom of the push-button is going to do a pull-down to ground. So I'll wire that up. I want that to be centered so it looks nice, and then I'll wire up the pull-up resistor. So there's my user push button switch. Okay, next thing and the last thing is to place our AES. Oops, I forgot. I need to create, because we don't have them, some 220 ohm dropping resistors for the LEDs. So actually, I do a search and there's nothing in the library. So I'm searching manufacturer part search, and I narrow down my search to resistor 220 ohm 0402, and there's tons of them available ready for download that I can place directly or acquire them into my own library. I'll pick the one at the top of the list because there's plenty in stock and it's a cheap price, and I'll choose the nominal footprint again, and I can place it directly. Now I'll set the comment, because I prefer to show the value, to 220 ohm. Note that I can use an ohm symbol there if I want. You can have Unicode characters in any parameter field, and I'll insert those into the RGB drive lines. And just quickly to neaten that up a little, I'll move that over, spread them out a little bit just by dragging. And you'll see also when you drag and move things in the schematic that the schematic validation is always running, and it shows you if you're going to modify the net list, it gives you a little warning sign or a green check mark if you're not making any electrical changes by the edit you're doing. So that's really helpful. So I'll just drag those around, tidy it up a bit. Okay, so now the final thing we need to do is find and place our encryption device, which is an ATAES132A, and there's none in my library, so I go to manufacturer part search, and we can find plenty of information about the supply chain, but also in the Altium cloud services, there's no symbol or footprint available. So what we're going to do is go back to the components panel, and we're going to create a component here, and I'm going to place it in the memory folder of my library because it's an EEPROM. It's an encryption EEPROM. So I'll put the part number in up here again, and automatically it also searches that, it lets me narrow down the search and automatically pulls that information from the supplier search online, and it automatically adds links to the data sheet, the manufacturer web page, supply chain preferences. And all I need to do is populate a few of my component templates missing data fields. So I'm saying this is a SMT device. It's 8 pins, 500 milliwatts maximum power dissipation. It is RoHS compliant and has a 1 megahertz SPI bus clock. So I add all that information in, and now we need to create a symbol. Now I could create a new symbol from scratch, pick an existing one from the database, or use the wizard. And the wizard, why not use the wizard? It's always better. There's a whole lot of options here that for different styles. But one of the things I love the most about this wizard is we can just paste pin table information directly, which I happen to have on my cursor already there. And it automatically positions the pins, orients them, names them, specifies their electrical type. All I need to do now is set the default designator for the symbol and save that. And now I've got my perfect schematic symbol ready to go. So I'll do the same thing now for the footprint. I'll run the wizard, and we're going to make an SOIC8 footprint. Note that all the IPC 7351 series parts are available, and it gives you a preview. I've run this before, so it remembered all my settings, which is nice for an SOIC8, so I don't need to change any of those. What I will do is enable the step model preview. So instead of getting a basic extrusion, I get a really nice detailed step model. Then there's some other options in the wizard there to change, toe and heel sizes, and add optionally, control or override other things. I'm just going to stick to all the IPC standard defaults and add my basic name description and finish that. And then there's my beautiful, perfect IPC standard footprint. I will just make one change. I'll get rid of that dot on the silk screen and mark pin 1 by actually making pin 1 rectangular instead of rounded. And there it is, a beautiful SOIC8 done in seconds. Now back to the actual component. There we've got the parametric data, the symbol, the footprint. All we have to do is release that into the library. So we're releasing it now. If there were any issues with the component, warnings would show up, but nothing came up because we made a full complete component. And now it immediately shows up in my library or components panel. So all I have to do is place it and wire it up. So I'm wiring up the VCC and then the ground and the rest of the SPI bus signals. So there's master in, slave out, master out, slave in, and SPI clock, and the chip select was already there. So that's the entire schematic of my dongle done. Now all I have to do is annotate everything, and I'll just use the default quiet annotation tool because it, there's a lot of other controls you can have over annotation if you want, but for this design it's a simple design, so we don't need to go to any great lengths. Now I want to update using the engineering change order and move everything into the PCB. The change order process in Altium Designer is not instant. It actually gives you an option to preview all the changes and cross-probe and select what you want to allow to change and what you don't. So there's all the parts moved into the board, and the next thing I want to do is change all those designator fonts. So I'm going to use a tool called Find Similar Objects, which makes it super easy to edit groups of things at once. I'm going to set all of those to true type font and make them all 1.2 millimeter font height, and that gets the designators to the right size I want for this design, which is really nice. You can change a lot of things all at once in a very controlled manner in Altium Designer. It's very powerful. Okay, and just to go back here, I can show you that 3D model of the enclosure obviously is pre-done with a hole for the push button to go through. And I could eyeball it like this, but later on we're going to place that using a precise technique, using a file that has some XY data in it. But one of the other cool things I really love about placing parts in Altium Designer is you can select them in sequence on the schematic like this, and then on the PCB side you'll see those same parts are selected. And there's this really cool tool here that remembers the sequence that I used in schematic to select them, and I can come here to component placement and rearrange them, and it places them on the cursor in that same order, so I can go about my business placing them in a more or less ordered, intelligent way and rotate them and orient them. You'll notice that I have a smaller degree for rotation in my preferences here. You can of course adjust that so you can place things at any kind of angle you want. There's the crystal there. So I'll place a few of these things, just using the spacebar to rotate them. Okay, like so. And then, we don't have too much time here. I want to get through this and do it quickly. So rather than place all the parts by hand, I'm going to just use a real shortcut trick here and use this feature called Place from File. And I have a predetermined pick and place file where I'd rearranged this earlier. So I hope you don't mind me playing a little trick there, but it does save us quite a bit of time. So all the parts, maybe there's a couple that I want to rearrange here still, where I'd swapped around their locations. So let's just place those. And that one needs to be rotated. And I'll just adjust a couple of things. A few minor tweaks here. These parts here, I need to rotate those as well. For those load caps. And I want to move the designators. I'll do more designator tweaking later on after we've routed the design. Okay, so that's pretty much it there. I'll save that. Okay, now what I need to do is obviously start routing the board. And I've already got design rules from the template. And so you see we've previously set up our clearance rules. The default rules all give you a basic set for basic board design, but I've already made this suitable for USB in my template, and I've even added a differential pair rule with a differential impedance profile that suits USB 2.0. And how that works is, here in the layer stack manager for the design, I've predefined the layer stack that uses Oshpark's 4-layer prototyping service, and I've added in all the details according to their specifications as a manufacturer, and I even have defined a 90 differential pair 90 ohm and single-ended 50 ohm, which I can reference in design rules. So let's go ahead and start by routing the USB differential pair. And there's all sorts of different options here, but you can see it's going to hug around other things, and I can do it that way. Let's say I wanted to make that more curvy. I can select that and hit tab to select the whole connection, and I can use this glossing feature, and the glossing is making that really beautiful routing there. Of course, I could do that interactively while I'm doing that. Now, if I want to change the width, say, of the power supply, I can do that by hitting tab and adjusting that as I'm going in the properties panel to the right there. So I'm going to fan out some grounds here because I'm going to put the ground layer, the next layer down, I'm going to have a ground polygon. That's how I'm planning my design. So I'm going to fan out some of those ground nets, just using a quick shortcut to place my rule-defined via. And of course, this net here, which is the shell of the USB connector, and some a resistor and capacitor to short out any static discharge that might happen when the user holds the device. And now grounds for the other side of that, and the power supply ground from the USB connector, those are all going to connect into that TVS chip that protects from voltage surges from the connection. Oh, and that capacitor needs to be rotated. I forgot to do that before. And so we'll connect up some of these grounds. Again, just wiring up the decoupling caps and some of the ground pins. So to fan out ICs, I like to use this really neat trick, which is to use the multiple route tool. I could carry on routing those signals on the next layer down, of course. And control double click on a net wire auto routes that trace and does a beautiful job, I might add. Really elegant, super quick and easy. Just control double click, done. And some of these need fanning out. Actually, I think I want to swap around. Let's see. I think I want to swap a couple of resistors over here to different positions to make the routing a bit easier here. So rather than, I can fan out that to ground. But this one, I think, needs to connect down here somewhere. So I'm going to swap that R5 and the R4 over. Let's see. I might unroute that. I'll just select a wire segment and control delete deletes the next segment along to it. So there's some other cool shortcuts and things that you can learn. And notice that when I drag this resistor R4, it takes its fan out trace and via with it. So even if you've fanned out an entire BGA, if you need to just move it a bit, it takes it. It's particularly good for small components like decoupling caps and resistors like this one. Let me just gloss that. It can take those things with them to save you a lot of time. Let me fan these ones out using Route Multi. Just click there and hit 2 to place down some vias. And up here now, I just want to keep adding some V-bus and ground vias around the place. I'll just fan out these signals on this one. Hit the 2 key, dumps down some vias, and I'll escape to stop that. So those are done. Note that my vias are further apart just because of the OSHPARC design rules for via hole-to-hole spacing. There's a few more here. I need to place I'll just connect that one into ground. I haven't even placed any planes or polygons yet, but that'll come later. These V-buses can all connect together. And all of this is pulling the trace widths and clearances from my existing design rules, so I don't have to, remember every single little detail. That one I don't want to be so wide, so I'm just going to set that to be 5 mils because it's just a signal net. And now I'll wire up the crystal again. That only needs to be 5 mils. Control click finishes the trace for me. I had the wrong net wire set there. So I made a mess of that. So what I'm going to do is use the gloss. I'll just select those and hit tab to select the whole connections. And gloss has made this beautiful curvy, neat and tidy. And I can edit it afterwards as well and push things around a bit. Anyway, not to spend too much time on that. That's going to work just fine for my purposes, only 12 megahertz. Anyway, next, what do I need? I need a ground up here for my EEPROM. So I'll plop a ground via down there. Control click to wire up ground on the switch. And moving the mouse around while you're routing influences how, you know, the algorithm will walk around and do other things. And again, if you don't want extra, or I didn't mean to move that switch. Oops, let's undo that. By the way, there's a huge redo and undo stack in Altium Designer. You can keep undoing and redoing to your heart's content pretty much. So you see, when I glossed that, it also glossed that other trace on top and made the whole thing like a nice beautiful little arc there. Now I'm going to place my ground polygon on the next layer down, and I'm not even going to try to replicate the board shape. I don't have to work so hard to do that. I'm just going to pour all over the whole thing to ground, and there's already some ground vias in there. So once I set the net for the polygon, here's the polygon properties here from my other screen. So I set that. I'm going to say pour over all same net objects and remove dead copper, and I click OK, and let's do that again. Let's right click on that and have it repoured. Actually, let me just check that I do have some. Yes, I have some ground vias in there. So polygons, repour all. And there it is, but it's flooded across the outside of the board. And normally your fabricator will say, we don't want you to put copper right across the edge of the board. So what I'm going to do is use this neat tool to create a keep out from the actual board shape. I'll make it 0.2 millimeters thick, and it's going to follow the route tool outline. So that creates a keep out, which is on the keep out layer, which you can't see right now. It's hidden in the background, but it is there. And I repour, and then the polygon only pours up to the keep out, maintaining an electrical clearance based on the design rules. So that's a neat, tidy way of doing grounds and power polygons on any board in Altium Designer. Now, I'm going to copy that polygon, which is ground, to my top layer. So I'm going to use a special thing called paste special and say paste on current layer to put it on the top layer with the same reference point, so it's in the same position exactly. Only this one I'm going to assign to VBus. So that's my VCC net essentially on this design. And I'm going to repour this polygon. And so there's my VBus. Right? So all my VBus connections are made. And I can still see that the board's not completely routed because I can still see some unrouted nets there. So there's still a little bit of fan out I need to do here, a little bit of routing, and a few more ground vias placed here and there. So I'm going to, let's fan out these nets. Actually, let's do these ones using route multi. Just place a via down. Yeah, that'll do. And of course, that's shorting out to the polygon, but we'll repour that in a moment. It's no big deal. And I'll just route this one. Actually, that's too thick. I don't want it that thick. So let's make that a 5 mil trace. And note, I can change routing corner modes, and it's automatically, even though the polygon's there, it knows I'm going to repour later. So it's just clearing the other objects that it needs to clear. And I don't need that via, because I actually was able to do that on the top layer. Let's just repour that real quick. So there's maintained the clearance. There's still a few more signals needed to get down here. So let's see, what do we got? We've got the SPI bus and the LED drive signals. So I'm just going to select all of those using Alt-click drag. Right, and now active route. I'll let active route do the job on layer 2 and top layer for the ones that don't have fan out vias. And that active route followed the last glossing option, which was any angle. So that's why you see any angle traces inside the board there. And that's the whole board done. There's a few ground and other signal nets still needed. So let's re-pour, or actually we'll shelve or unroute all the polygons. Shelving them puts them in memory so we can restore them later. Now I want this via to look like the vias I've already used. So note that I can choose that. That automatically becomes a via template when I place a via. So I can very easily select it and reuse it for either stitching or fanning out by hand, which is what I'm doing here. I'm going to place, that one will be V-bus, another V-bus can go there. Got some ground vias there. Here's a V-bus here, because one of the other layers I'll place a V-bus polygon plane as well. I'll place a ground via here. Let's see, we're going to need one there. Probably, yes, I've got these pull-up resistors over here, so I'll place a couple of V-bus polygons over here. And while they're, vias, while they're selected, I'll assign them to V-bus. Right? Oh, and I don't want that trace tag there. I'll just wire those up straight up and delete that one. Okay, now let's see. What else do we need? This. Let's see that. I want to add a proper trace in there. Oh, and that V is not assigned yet to ground. So let's do that real quick. Okay. Now this one needs to be attached. That's the decoupling for VUSB inside the chip. What else? Those two vias need to be assigned to the bus voltage. So let's select them. Assign them to VBus. Okay, and the polygons will connect into those, so we'll let that happen. Let's see what we've got right now. So the polygon floods over the vias that are assigned to it. Haven't quite finished all the routing yet, but we'll come back to some of that in a moment. So we re-pour the polygon. Let's wire up that ground. I have to re-pour again so it doesn't short out. Okay. All right, so there's a power and ground polygons taken care of on the first two layers. I've done this whole board in just 2 layers. Really, I could do it in 2 layers, even though I'm using a 4-layer template. So I'm just going to copy the ground to the inner layer 2, and the bottom layer can just be another VBus or VCC, so we get a little extra capacitance and better EMI performance. Basically, the whole board is now completely shielded. And that's what it looks like. That's complete. That's the whole thing done. There is just one thing, and if you're observant, you've noticed there's one unrouted net, which I still need to get to. Don't worry, I'll get to that. Meanwhile, let's fix up all this silk screen. So we need to move. And notice how, as I'm dragging these silk screens around, it's dimming everything else but highlighting the part that designator belongs to. I find that particularly useful, so you don't get confused. And I'm switching into single layer mode where it's grayscaled every other layer. That's just a single Shift-S shortcut in Altium Designer. So it's super easy to get in and out of single layer mode or to just look at one layer. Okay, that's R1 is up there a bit higher. Where is R1? Oh, it's that one there. Okay. And C6 is this one, and C5 must be right under it. C1 is over here. U1, I want that right reading. Now the LED, DS1, R4 is down here, then R6 and R7. And of course, there's alignment tools. I'm eyeballing all this and doing it by hand because I'm just comfortable doing it that way. But there's, of course, many alignment tools where you can group select a bunch of designators and say, align all these up together to the same neat and tidy line. And you can do that with not just with designator fonts, but with any object in PCB actually. Okay, so there's my designators, and just as a quick eyeball, I go to 3D mode, and what I like to do is actually turn off all the 3D models and just look at it, so I'm looking at the board like it's a completed board with the silk screen, because that's a really good way of seeing instantly when you've got silkscreen objects over solder mask openings and things like that. So there's that final net. I'll re-pour all the polygons. That board is complete, and it's only been, what, 35 minutes start to finish. Of course, we still want to generate some manufacturing outputs, right? And we could run a design rule check. Just to save time, I'm not actually going to run that. I know this is all done according to my rules interactively. So normally the next thing you'll want to do is add some assembly and fabrication drawings to your design. So I'm going to do that right now and pull also from a template. Of course, you can start these from scratch, but I'm using a template because I like to keep the same standard set of drawings that I know the fabricators I work with want to see. So I've created my fab drawing, and it's automatically pulled in the different layer views, the layer stack table, any notes, and of course I can tweak and adjust those, so I'll save that. Okay, and finally, the last thing we want to do is release the project. So what releasing does, and whether you're using a data management system or not, you can do this, it generates all the manufacturing and assembly outputs in a batch process. So this can save you a lot of time as well, and this whole thing can be tweaked and templated if you like. Altium Designer automatically generates the basic outputs that you need for every design, including Gerber, ODB++, and you can see in here, it's automatically selected the layers we need to generate extended Gerber and NC drill files. And if you want, you can add and customize this to use IPC or Gerber X2 or ODB++, depending on what you prefer. And we're just going to quickly generate those fab and assembly outputs. And I can do that now. It's even going to generate PDFs. I'm going to hit preview, and this will show it's actually going to go ahead and run those output generators in a batch. So I get one cohesive set of data from this revision of my design. So there's never, ever going to be any confusion anymore about, well, this Gerber file was from what version of the PCB, and did we make any changes since then? And no, those days are gone. Now we can create one data package for handoff to manufacturing that is complete and unambiguous. And we get all the Gerbers, and if I click view on that, it opens it in the CAM editor, Camtastic, right in Altium Designer. That's the actual Gerber files generated from this design. I can even open a panel here in the CAM editor, which is a fully fledged CAM editor. You can do anything you need here. You can do DFM checks. And I'm actually going through, you can single out the layers and look at the actual image data from the Gerbers. You could consolidate this with drill data. You can even, I won't go through it, but you can even reverse engineer boards from Gerbers and drill files to actual PCB documents if you want. And there's the PDF of my basic assembly layer drawing or fab drawing. And that's it.